In this video, I'll be solving several problems involving momentum, conservation of momentum, and impulse. So for our first problem, we're given a system of two particles and we're asked to find the components of the net momentum. So we want to find the momentum component-wise. So we'll start with the x component of the total momentum of the system. So this is big capital P sub x. And we're going to get the x component of momentum from the first particle plus the x component of the momentum from the second particle. So maybe I'll call this one particle 1 and this one particle 2. So the first thing to notice is particle 2 is only moving in the y direction. So that means its momentum is 0 in the x direction. So for the total momentum in the x direction, it's just for particle 1. And it's going to have a negative x component, so I'm going to make it negative. And this is the mass of the first particle times the velocity of the first particle in the x direction. So if we make our right triangle, where this is the momentum of the first particle, and this is our angle, this will be P1y, this will be P1x, and so P1x is the adjacent side, so that means it'll be minus m1 v1 cosine of 50 degrees. And if we plug that in, we get minus 2 kilograms times 8 meters per second times cosine of 50. If we plug that in, we get minus 15.4 kilograms meters per second. Then we can do the same thing with the y component of momentum, except now both of our particles will contribute to the momentum. So the first particle is going to have a positive y component. It'll be m1 v1y. And then the second particle has a downward momentum, so it'll be minus m2 v2. And I'm just going to write this as v2 since all of the velocity is in the y direction. But then I need to write the y component of the first particle. So since the x component was cosine, the y component will be sine of 50 degrees minus m2 v2, 2 kilograms times 8 meters per second, sine of 50 degrees, minus 3 kilograms times 7 meters per second. And if we plug all that in, we get minus 25.2 kilograms meters per second. In the next problem, we have a 1,000 kilogram car that is traveling at 60 meters per second. And we want to find the speed that a 150 gram baseball would need to travel in order to have the same momentum and the same kinetic energy as this 1,000 kilogram car. So first, we need to find the momentum of the car. So the momentum of the car will be the mass of the car times the velocity of the car. So that will be 1,000 kilograms times 60 meters per second, or 60,000 kilogram meters per second. So now for the baseball, the momentum of the baseball will be the mass of the baseball times the velocity of the baseball. And we know what the momentum needs to be. We want the same momentum as the car, and we know the mass of the baseball, so we need to solve for the velocity of the baseball just by dividing by m. And so then we can plug in 60,000 kilogram meters per second over 0.150 kilograms. And that will give us 400,000 meters per second, or 400 kilometers per second. So you have to throw it really fast. For the kinetic energy, we need to do the same thing. So we need to find the kinetic energy of the car. So that's going to be 1/2 the mass of the car times the velocity of the car squared, or 1/2 1,000 kilograms times 60 meters per second, all squared, and that will be 1.8 times 10 to the 6 joules, or 1800 kilojoules. So now we can do the same thing with the baseball. The kinetic energy of the baseball is 1/2 the mass of the baseball times the velocity of the baseball squared. And if we solve for the velocity of the baseball, we need to move the 2 and the m over, so multiply by 2, divide by m, and then take the square root. And if we plug all of that in, the kinetic energy we got up here, 1.8 times 10 to the 6 joules over 0.150 kilograms, we'll get 4,900 meters per second, or 4.9 kilometers per second. In this problem, we have a bullet with a mass of 5 grams, and it is shot horizontally at a 2.2 kilogram piece of firewood at a speed of 400 meters per second. The bullet passes through the wood and comes out the other side with a speed of 144 meters per second, and we want to find the final speed of the firewood. So the bullet and the firewood together are going to be our system, and we know for a closed system the momentum is conserved, so the final momentum of the system is equal to the initial momentum of the system. So we're going to use conservation of momentum. So we have the momentum of the firewood plus the momentum of the bullet, and then on the initial side we also have the momentum of the firewood plus the momentum of the bullet initially. And initially the wood is not going to be moving. We're shooting a bullet at a piece of wood that is sitting still, so the initial momentum of the firewood is 0. And now the mass, we can plug in our definition for momentum, so we get the mass of the wood times the velocity of the wood plus the mass of the bullet times the final velocity of the bullet is equal to the mass of the bullet times the initial velocity of the bullet. And now what we're looking for is the final velocity of the wood, so we just need to solve for it. So I'll move this second term over. So get the mass of the firewood times the velocity of the firewood at the end is equal to the mass of the bullet times the initial velocity of the bullet, and now minus the mass of the bullet times the final velocity of the bullet. And now I can divide by the mass of the firewood, and I'm going to factor out mass of the bullet just to make it easier to plug in. Divide by the mass of the firewood. And so now, if I plug all these numbers in there, I'll get 0.005 kilograms for the mass of the bullet times 400 meters per second minus 144 meters per second. So how fast the bullet's going initially minus how fast it's going at the end, all over 2.2 kilograms, the mass of the wood, and that gives me the speed of the wood as 0.58 meters per second. For the next problem, we have a 0.8 kilogram ball that is not moving on a flat table. A second ball with a mass of 0.5 kilograms is moving to the right at a speed of 2 meters per second before colliding with the first ball. After the collision, the 0.5 kilogram ball has a speed of 1.6 meters per second at an angle of 36.9 degrees below the x-axis. And we want to find the magnitude and direction of the velocity for the 0.8 kilogram ball after the collision, and then we want to find the total change in kinetic energy of the two-ball system. So I'm going to draw a picture, and this is always good with any conservation law, to know what's happening before and what's happening after. So before the collision, in this case, we have a 0.5 kilogram ball that's moving to the right, and it's going to collide with a 0.8 kilogram ball, and I will call the first one A and the second one B, so we can kind of choose our labels in such a way that it makes sense to us. And then the velocity of this one is 0. And then after the first one is going to be going down or below the x-axis at an angle of 36.9 degrees and with a speed of 1.6 meters per second. And we want to know magnitude and direction of the other ball. Okay, so this is question mark 2. So what we want to do is use conservation of momentum. So in this problem, first of all, I noticed that it's originally in one dimension, but then when they collide, they're going to go off at angles, so it's in 2 dimensions. And since momentum is a vector quantity, I'm going to want to break it into components. So I'm going to start with the x component first. So I have the final momentum in the x direction for the whole system is equal to the initial momentum in the x direction for the whole system. So I will have the final momentum of A in the x direction plus the final momentum of B in the x direction is equal to the initial momentum of A in the x direction plus the initial momentum of B in the x direction. So I like to write all of my subscripts. It's tempting, since you know everything here is in the x direction, to just drop it. But we don't want to forget to take the x and y components of our velocity, and we don't want to confuse those components with the actual hypotenuse or the vector magnitude itself. So it's good to always keep your subscripts. And the first thing we want to do is get rid of the initial momentum of B, since it's 0, since it's initially not moving. So this will give us the mass of A times the final velocity of A in the x direction plus mb times the final velocity of B in the x direction. And that's all equal to the mass of A times the initial velocity of A in the x direction. Okay, so now we want to solve for VBFX, but we also need to find the x component of the final velocity of A using this triangle. So if we do that, we'll get MA VAF, and the x component is adjacent to this 36.9 degree angle. So adjacent means this will be cosine 36.9 degrees. And then plus MB VBFX equals MA BAIX. And now we're ready to solve for VBFX. Okay, so if we do that, we'll get VBFX is equal to MA, and then I'm going to factor out this VAIX, and then when I move this term over by subtracting, I will get a minus VAF cosine of 36.9 degrees. And then I need to divide everything by MB in front, so I'm just going to put that out front. So when I plug that in, I'll get the mass of A over the mass of B, which is 0.5 kilograms over 0.8 kilograms, times the initial velocity of A in the x direction, but it's all in the x direction initially for ball A, and then minus the final velocity, 1.6 meters per second, times cosine of 36.9 degrees. And when we plug that in, we get 0.553 meters per second. So now we need to do the y direction. So I'm going to erase all of this, saving my VBFX. So I'll move this somewhere safe, and then I will move on to the y component. So for the y component, we'll want to do the same thing. So we have PF in the y direction is equal to pi in the y direction. So at the end, we have p a final in the y direction plus p of b final in the y direction is equal to PA initial in the y direction plus PB initial in the y direction. But neither of them are moving in the y direction initially. So particle B, or ball B, is not moving at all, and ball A is only moving left and right. So it's moving to the right or all in the x direction. So the y component momentum is 0. So we have the mass of A times the final velocity of A in the y direction. But again, this is just going to be the opposite side of this triangle, or times sine of 36.9 degrees. We also can see that it's going down, so it's going to be negative, plus mb times the final velocity of b in the y direction, and that's going to sum to 0. So now we can solve for our y component. So this is going to be VBF, y component. We're going to move everything over, so we'll get plus a VAF sine 36.9 degrees all over MB. So if we plug that in, we get 0.5 kilograms times final velocity of A, or 1.6 meters per second, times sine of 36.9 this time, all over 0.8 kilograms. And if we plug all of that in, we get a 0.60 meters per second. Okay, so now that we have that, we can find the magnitude and direction. So I'll move this again somewhere safe. And now we can use the Pythagorean theorem to find VBF, the magnitude. So we just take the square root of VBF x squared plus VBF y squared, or 0.553 meters per second all squared plus 0.6 meters per second squared. If we do that, we get 0.816 meters per second. So we'll round that up to 0.82 meters per second. If we want our direction, then we just need to do inverse tangent of VBFy over VBFX. So if we plug that in, we get 47.3 degrees. So now our final answer is, for the magnitude, 0.82 meters per second at an angle of 47.3 degrees. And now we can do part B and find the change in kinetic energy. So this part B. So initially the kinetic energy is only due to particle A, so we have 1/2 ma times VAI squared, or 1/2 0.5 kilograms times 2 meters per second all squared. And that's just going to be 2 squared is 4, 1/2, or 1 joule. If we look at the final kinetic energy, we have both of them moving, so we have 1/2 ma VAF squared plus 1/2 mb VBF squared, which we just found. So this will be 1/2 times 0.5 kilograms times 1.6 meters per second squared plus 1/2 0.8 kilograms and 0.82 meters per second all squared. And if we plug all of that in, we get 0.91 joules. So now we can find the change in kinetic energy, or Kf minus Ki, and that will be 0.91 joules minus 1 joule, which equals minus 0.09 joules. So we lost energy in this collision. The next problem, we have a box weighing 19.8 newtons that is moving to the right at a speed of 4 meters per second. It collides with another box with a mass of 3 kilograms that is not moving. After the boxes collide, they stick together and travel up a frictionless ramp that makes an angle of 30 degrees above the horizontal. We're asked to find the final velocity of the two blocks right after the collision, and then find how high they will travel up the ramp. So, for part A, this is going to be a collision, so we'll use conservation of momentum. So we have the final momentum is equal to the initial momentum, and at the end they're going to stick together and collide and in the end they're going to stick together. So this is an inelastic collision. So they'll be moving together at the end at the same velocity. So we'll just combine their masses and multiply that by VF. And this is going to equal mass A times VA initial plus MB times VB initial. But VB is not initially moving, so its momentum is 0. And now we can solve for VF, the speed at which they're both moving after the collision, just by dividing by MA plus MB. So we get MA over MA plus MB, all times VAI. And our mass A was not given to us, but we were given the weight of box A. So this is going to be the weight of A divided by G. So if we just do that, we'll get the mass of A is 19.8 newtons divided by 9.8 meters per second squared, or 2 kilograms. So now we're ready to plug in. We have 2 kilograms for mass A over 2 kilograms plus 3 kilograms, all times 4 meters per second. And that will give us 1.6 meters per second after the collision. So now for part B, you have two options. You can either use kinematics, or we can use energy. And I prefer to use energy anytime I can. So we're going to do conservation of energy, which says the final energy is equal to the initial energy. So that means we have kinetic energy plus potential energy at the end, and that's equal to the initial kinetic energy plus initial potential energy. Okay, so in the beginning, they're both on the ground, so there is no gravitational potential energy. There's no spring, so there's no elastic potential energy. And at the end, when they get to the top of the ramp, they're eventually going to stop. So since they're not moving at the end, their final kinetic energy will be 0. So now I'm going to write their masses as big M, since they're all moving together. So big M will be the total mass, MA plus MB. So we get big M times GH equals the initial kinetic energy, or 1/2 big M VI squared. Okay, so now the beginning of this part of the problem, they have already collided and they're moving together. Okay, so the beginning of this problem is when they're right here and they're together as one. So we can see that our masses are going to cancel, so that's nice. And now we can just solve for our distance, except now we need to find this distance L, but in our equation we have h, which is the height. So since we're given this angle of the ramp, we need to find h in terms of L. If we do that, h is the opposite side, so h will be the hypotenuse L times sine of this angle, which is given to us as 30 degrees. So now we can move everything over and plug it in. So we'll have G times h, which now we know is L sine 30, is equal to VI squared over 2. And if we solve for L, we'll get VI squared over 2G sine 30 degrees, or 1.6 meters per second, which is our final velocity from the last part. It's now our initial velocity when we get to the bottom of the ramp. That squared over 2 times 9.8 meters per second squared times sine of 30 degrees. If we plug all that in, we get 0.26 meters up the ramp. In the next problem, we have a softball catcher weighing 550 newtons that is crouched on a frictionless frozen pond. They catch a softball going a speed of 3.6 meters per second. If the catcher and the softball move at a speed of 0.013 meters per second, use conservation of momentum to find the mass of the softball. So it tells us we want to use conservation of momentum, so that means the total final momentum is equal to the total initial momentum. So we have the momentum of the catcher at the end plus the momentum of the softball at the end. It's equal to the initial momentum of the catcher plus the initial momentum of the softball. So initially, the catcher is not moving, and when the catcher does catch the softball, they're going to be stuck together. So it's going to be stuck in their mitt. So we'll have at the end the mass of the catcher plus the mass of the softball all moving together at the same final velocity. And that'll equal the mass of the softball times the initial velocity of the softball. So now we want to solve for the mass of the softball. So we need to distribute our final velocity to pull out the mass of the softball. So the mass of the catcher times VF plus mass of the softball times VF is equal to mass of the softball times the initial velocity of the softball. So now I can move this term over to get the mass of the softball by itself, and I'm going to move it to the left. So I have the mass of the softball times V initial of the softball, and then when I move MSVF over, it'll become negative, so I'll factor out MS and have final velocity as negative equals what was left on the left side, or the mass of the catcher times the final velocity. And then solving for the mass of the softball, I'll have the mass of the catcher times the final velocity of both of them, all over the initial velocity of the softball minus the final velocity. Okay, so before I can plug all of this in, I was given the weight of the catcher in newtons. So the weight of the catcher is the mass of the catcher times gravity, or 550 newtons. So this means the mass of the catcher will be 550 newtons divided by g, or 9.8 meters per second squared, or 56 kilograms. So now I'm ready to plug in. I have the mass of the softball is 56 kilograms times the final velocity, which is 0.013 meters per second. So moving kind of slow. All over 3.6 meters per second minus 0.013 meters per second. And that's going to equal 0.203 kilograms, or 203 grams, which is about the size of a softball. In the next problem, we have two billiard balls that collide elastically after moving in toward each other in exactly opposite directions. They're moving along the x-axis, and the first has a mass of 3 kilograms and initially moves at 2.5 meters per second, while the second has a mass of 5 kilograms and initially moves at 2 meters per second. And we want to find the velocity of each glider after the collision. So in this problem, we're going to use a little trick. So I've already drawn the picture. We have our first ball going to the right, the other one is going to the left, and I put in that it had a negative velocity since I drew it going to the left. You could have swapped these and had A on the right, B on the left. It's up to you, as long as you're consistent. And what we want to do is we want to use these equations that we have for the final velocity if an object A collides with an object B when object B is at rest. Okay, if we do that, then we get the final velocity of object A is the mass of A minus the mass of B all over the sum of the masses times the initial velocity of A. So this is an equation that you would be given or you could look up, and it's derived using conservation of energy along with conservation of momentum. Okay, but in this problem, object B has an initial velocity. So we can do this trick where if we add a certain amount of velocity to object B to make it 0. So in this case, we would need to add 2 meters per second to VB initially. We'd also need to add it to VA initially. Then we can treat it as though VB is at rest. Okay, so we can kind of just shift the velocities such that it looks like object B is at rest. Okay, so now this is plus 2 meters per second, and this is plus 2 meters per second. Okay, so now we can plug all of this in. Mass A is 3 kilograms minus mass B, 5 kilograms, all over their sum, which will just end up being 8 kilograms, times the initial velocity of A, but now we've shifted our velocity by adding 2 meters per second, so that's going to be 2.5 plus 2, or 4.5 meters per second. Okay, and then we get minus 1.125 meters per second. Okay, so it kind of makes sense that object A is moving to the left after the collision, so it's negative, so that makes sense. But now that we've done this, we can't just leave it the way it is. We have to subtract that 2 meters per second that we added. So now subtract 2 meters per second, and we get that our actual VAF is minus 1.125 meters per second minus 2 meters per second, or 3.125 meters per second. So there are other ways you could solve this problem, but this is a really convenient way that we get to use these equations that we've already derived by just shifting our velocity such that it looks like object B is starting at rest. So now we can do the same thing with object B. So the equation for the final velocity of B, which again was initially at rest, is equal to twice the mass of object A, again over the sum of the masses, times the initial velocity of A. Okay, and so if we plug in, we'll get 2 times 3 kilograms, all over 3 kilograms plus 5 kilograms, times the initial velocity of A, which again now is still shifted, so it is 4.5 meters per second, and that will be 3.375 meters per second. And again, in order to use these equations, we have added 2 meters per second, so now we need to subtract from our result, and we get the final velocity of B is 3.375 minus 2 meters per second, and that gives us 1.375 meters per second. In the next problem, we have a car weighing 10,000 newtons that's going 80 miles an hour, and we're asked to find the impulse and the average force exerted on the car if it crashes into a tree and stops in 0.5 seconds. So we'll start with our equations for impulse. So impulse is equal to the average force times the time interval over which that force is acting. And the impulse is also equal to the change in momentum. So this comes from Newton's second law. And the change in momentum, this is just PF minus PI. Okay, so the first thing we need to do is get our 80 miles an hour into something we can use, so meters per second. So if we do that conversion, we will end up getting 35.76 meters per second. And we also need to get our 10,000 newtons. We need to find out how much mass this is, so this is equal to mg. So mass is 10,000 newtons over 9.8 meters per second squared, or 1,020 kilograms. Okay, so now we want to find the average force, but we don't know the impulse yet, so we cannot use this equation because both of these things are unknown. So we can find the impulse using our second equation, or the change in momentum. So the impulse is equal to PF minus PI. But if the car crashes and it stops, then the final momentum is just going to be 0. So this leaves us with minus the initial momentum, or minus mvi, which is minus 1,020 kilograms times our velocity, 35.76 meters per second. And that equals 36,475 kilograms meters per second. Okay? Or we could write this as 3.6 times 10 to the 4th kilograms meters per second. Now that we have our impulse, now we can use this second equation and rearrange for our average force. So the average force will be the impulse over the time interval. And so that will be, I'll use the unrounded version of my impulse over the time interval of 0.500 seconds. And we get an average force of 72,950 newtons, or 7.3 times 10 to the 4th newtons, or 73 kilonewtons. In the next problem, we have a football player that kicks a 450-gram ball vertically upward, and we want to find the impulse imparted by the football player to the ball if it reaches a height of 8 meters. So we have a ball that's getting kicked upwards. Okay, so it's eventually going to go a height of 8 meters. And so first we need to figure out how fast it's going down here. So we need to find the initial velocity down here in order for it to go through this distance of 8 meters. So to do that, we can start off using conservation of energy. So we'll use E final equals E initial. So the total final energy is the sum of the final kinetic energy plus the final potential energy, and that's equal to the initial kinetic energy plus the initial potential energy. But initially, we're going to say that the ball is at y equals 0, so it has no potential energy. And at the end, when the ball reaches its maximum height, it's going to stop. And so it's not going to have any kinetic energy at the end. So then we're left with just mgy final equals 1/2 mvi squared. So now our mass is going to cancel out since it's on both sides. And we can solve for the initial velocity that this ball is going to need in order to go this height. So vi will equal square root of 2gy final, or you might have the height, mgh, in here. Either way is fine. And this is the square root of 2 times 9.8 meters per second squared over the final height of 8 meters. And we get a speed of 12.52 meters per second. So now we know that the force from the football player, from his kick, is going to have to change the momentum of this ball from being at rest to going this fast in order to reach this height. So the impulse that the football player must impart will equal the change in momentum of the ball when he kicks it, which is equal to the change in its momentum, PF minus PI. And before the kick, the momentum is 0. The ball's not moving. Okay? And so the impulse is equal to the mass times the final velocity. Okay? And the final velocity after the kick, that was our initial velocity that we found before it went into the air. Okay? So this is equal to 0.450 kilograms, or 450 grams, times our 12.52 meters per second. And that equals an impulse of 5.63 kilograms meters per second. So this is how much impulse he would need in order to change the momentum of the ball such that it reaches 12.52 meters per second, and that's how fast it needs to go this 8 meters high. Okay, in our last problem, your rifle can accelerate a 7-gram bullet from rest to a speed of 850 meters per second If it does this in a time of 0.002 seconds, find the impulse and the average force on the bullet. So the impulse is equal to the change in momentum. So this is PF minus PI. The initial momentum of the bullet is 0 since it's not moving. So the change in momentum is just equal to the final momentum, or the mass of the bullet, times the velocity, the final velocity of the bullet, which in this case is 0.007 kilograms for 7 grams, and it's going to be going 850 meters per second. So this leaves us with an impulse of 5.95 kilograms meters per second. Now that we have the impulse from using the change in momentum, now we can find the average force by using our other equation for impulse. Impulse is F average times the time interval, or F average is the impulse over the time interval. And so F average will be our impulse that we just found, 5.95 kilogram meters per second, all over the time interval of 0.002 seconds, or 2,975 newtons, or roughly 3,000 newtons, or 3 kilonewtons. So I hope going through some of these problems on momentum and impulse have helped you, and I'll see you in the next video.